So this is going to be a lesson on inclined planes and how to use vectors to break down the components of weight that cause the box to slide down an inclined plane. So we're going to start out with an inclined plane, a ramp, put a box on it, and I'm going to start by drawing a force diagram. And the first thing we know is we have gravity, weight, and weight always goes straight down. And the second force that we know we have is support force, because the box is sitting on a surface, so there's a contact force there. But remember that support force is always perpendicular to the surface, the contact surface. So the support force runs this way. Now, the issue here is that the object, the box, is going to run up and down the plane, right? The direction of motion of the box would be up or down. So if you think about a traditional XY axis, the box would be moving both vertically and horizontally, which complicates the mathematics. So our way of getting around that and making life a little easier is to opt to rotate the axis. So what I mean by that is I'm going to set up my axis so that the x direction is parallel to the plane, parallel to the ramp, and the y direction is perpendicular. So first note to make, we know that we're making notes here, support force is perpendicular to the ramp, and I've chosen to rotate the axis so the x direction is parallel to the ramp. Now, what this leaves us with is a diagram that I'm going to break down into x and y vectors. So I'm going to redraw our diagram. Here's the inclined plane, make it a little bigger. We know that there's weight going down and support force going up. Now, because the weight is now in the xy direction, put the axis back in. Because the weight is in the x and y direction, I'm going to actually find how much of the weight is in the y direction, or this red line, and how much is in the x direction. I'll draw that in green. Now, the thing that's important to note here is the role of these different forces. So, weight in the x direction is the force that will accelerate the box down the incline, down the ramp. Wy is the force that runs opposite or cancels out the support force, or Wy will equal support force. I know that last little bit because the box is going to slide down the ramp. It's not going to fall through the ramp. It's not going to shoot up off the ramp. It's not going to accelerate at all in the y direction. So the net force in the y direction must be 0. So support force and weight in the y direction must be equal. So if I make a table, let's do it over here. I'm going to make a table looking at the forces, similar to what we've done before, with x and y columns. This is the x forces, these are the y forces. And in this particular case, I only have two forces to consider. I have weight and I have support force. And so now the question becomes, how do we calculate the force in the x direction and in the y direction for weight? So I actually need to go back up to my diagram and take a look at some of the angles involved. So we'll do those in pink. So if we draw this line here, typically inclines are measured by this angle. So let's suppose that's 30 degrees. Since weight goes straight down, this angle here is a 90-degree angle, and I have a right triangle, which tells me that this angle up here is 60 degrees. But I also have another right angle over here, because recall that support force is always perpendicular to the surface. So if I know I've got a 60-degree angle, and it is, was it supplementary to a 90-degree angle, basically we know that this whole line here, this is 180 degrees, this angle in here must be 30. So I want to focus in on the triangle that I will mark with right here, here, and here. If you look at that triangle, we can actually start to find out some of the values of weight x and weight y. Essentially, you have a triangle that looks like this. This is 30, this is W, this is 90, weight y, weight x. Let's make that thinner. So I can go ahead and write that weight in the x direction will be mg sine 30, and in the y direction, mg cosine 30. Now, the thing that's sometimes hard to wrap your mind around is the fact that sine and cosine have essentially switched. We typically associate x with cosine functions and y with sine functions, but notice that I'm actually not defining the triangle by the angle that we normally use. I'm using its complement, so the sine and cosine functions are switched. Now, in order to consider the force, the support force, I need to think about, go back to my diagram and look at the direction it's acting in. Remember, support force only acts in the y direction because we rotated the axis. So that means that the support force is 0 in the x direction, And you can just write plain old support force in the y direction. All of it is in the y. But what I do know is if I want to look at the net force, so I'm going to add these up. I'm going to make that last column the sum of the forces. In the y direction, the sum of the forces is 0. There's no acceleration in the y direction. There is some acceleration in the situation in the x direction, and it's going to be given by adding mg sine theta, or weight in the x direction, with the support force in the x direction, which is 0. So I end up with net force equal to mg sine 30. Or what I can do with this is I know that the net force of the box on the incline is going to be mg sine theta is the general, obviously, the general expression, but in our case, 30 degrees. Or for a 30-degree angle, the net force will be half of its weight that pulls it down the incline. This, of course, is assuming there's no friction. If there is friction, things get a little more complicated, but we can talk about that another time. Once you have the net force, you could then start to use things like second law, and we know that A is equal to the net force divided by mass. So in this situation, that would be mg sine theta all over m, or the acceleration would just simply be g sine theta. This, of course, is ax. These are all net forces in the x direction. We know that in this situation, ay is 0. We said that early on. Ay is 0. So these are the things we can pull away from a box sliding down an inclined plane.